the camera on our side so that we always see Anja, or can we do something like that?
When she starts talking, it's automatically like.
Yes. But each time she stops talking, it will flip.
So it's when we talk, I believe you said.
But I mean, yeah, she appears when she's.
Or will I stop it all?
No, the point is you want to hide non-video participants or something, but I think it's.
Yeah, but if there's no video coming from us, the only video will be hers, and therefore it will be the
Yeah,
one
let's
showing,
not
right?
break the setup. That's.
No, I think it's easier to keep it.
Okay.
That way.
Then, yeah, this is Anja's talk on verifying vampire proofs in the Pi calculus. Anja?
Am I good to go?
Yes, good to go.
Yes, okay, great. Hi, everyone. I'm Anja. And together with Michael and Martin, we did this really cool thing about verifying vampire proofs in Didacti. So Didactic concrete syntax of the Lambda Pi calculus modulo. First of all, I would like to really thank everyone for letting me do this talk remotely. I will steal, a couple of seconds of your time to one last time put on my gender balance coordinator hat of the EuroProofNet and telling you that I really appreciate it. I have a small child at home. I was unable to travel and I felt really supported by this opportunity. I know that Zoom sucks compared to being there in person, and I would have preferred to be with you. But I really appreciated this. And, among the authors, I'm not the only one with the same constraints. So Martin also wasn't unable to travel because of small children. And so you're not supporting just, gender diversity, but you're supporting everyone in the action. So I know it's suboptimal, but I really appreciate you giving me this opportunity. Okay, now my gender balance coordinator hat is off and we can proceed with the actual work. So I will start with something that you probably all know because you're all experts here. And this is, just give me a second. Yeah. How I see the two approaches of formal proofs, right? Two approaches to formal proving. One is the automated theorem prover, where we can be lazy because the machine will do everything for us, so we can chill on the couch. And the other one is the interactive theorem prover, when we actually have to roll up our sleeves, so to say, and do all of the work. But in return, we get some high confidence that what we did, what we proved, is actually correct, right? We have some form of verification in the background. So for this talk and for this work, the automated theorem prover, the ATP that we are using is Vampire. Just FYI, this is not a Vampire official logo. So don't quote me on that. It was one of the ideas circulated among the developers. So just for the sake of this talk, I'm using this one. You can see my pointer, right? Yes, okay, good. And the interactive theorem prover will be Didacti, which I'm pretty sure I don't have to sell you on. Most of you are familiar with it. Okay, now just briefly, so I'm assuming most of you are like Didacti experts, so just a few words on the automated theorem proving side. So I said we want to be lazy, so we just want to give you the input, the axioms, and the negated conjecture. Then we feed it to the machine, press a button, say a prayer, cross our fingers, wait some time, and if we're fortunate, we get a proof trace in the output, or maybe the thing that we're trying to prove is not a theorem, so sometimes we get the reason for that, or most of the time we are out of luck and we timed out, right? We don't want to wait forever. I want to talk to you specifically about this proof trace because the way it usually appears is it's some form of a sequence or a directed graph of first order formulas, because this is first order theorem proving. It contains information about which premises and which inference rules were used to get to each of the formulas. And in principle, they should emit enough detail to reconstruct the proof fully, as a human. You can see which part of the formula was eliminated and so on, and do some substitutions on your own. I used to think of the ATPs as some sort of a black box, and you can use them. You just like press a button and then you get a proof out. You don't really need to know how they work. And essentially, it's a very complex piece of software. So when I first talked to people who developed Vampire, I was surprised because, you know, I originally came from the ITP community, so to say, that the trusted code base is quite big. Essentially, you have to trust everything, or, you know, manually inspect the proof trace that we give you as some sort of a certificate. Now, the downside about this proof trace is that, at least so far, it wasn't machine checkable. So I wanted to do something about that. So the approach that we're doing here, so the big picture, right, is this translation of proof trace. So as input, we have axioms and the negated conjecture. We feed them to Vampire. We get some proof trace if we do, and in case we do, we want to translate it to an ITP, concretely deducti, in order to then verify it, that this is actually a proof, right? So our work is here in this translation of proof trace, and this is mainly what I will be talking about today. So why we're doing this, I know I'm preaching to the choir, so I'll go through this quickly. So basically, we want to find any unsoundness bugs. Bugs have been found, and some are likely still there. The most recent one I'm aware of is on January of this year. So admittedly, it's somewhere in a sort of obscure part of Vampire logic. So this combination was disallowed later on, but, you know, we got to a proof that we shouldn't have because it was false. So, you know, these kind of bugs are uncoverable by this approach in principle. We want to have higher degree of confidence in these proofs. So like I said, minimizing the trusted code base. And we want to have, as much as possible, interoperability of proofs. That's why we chose Didacti and EuroProofNet. The cherry on top would be to have potential to implement this as hammers in ITP. So to have a hammer that uses Vampire. Now, why Vampire? Well, short answer for me is, well, because it's the best. This picture here is, I will, you know, brag a little bit in the next sentence. This year at Kate, was the ATP competition. It's called CASC, and Vampire just won all of the trophies in every category. So I thought, you know, where to start better than somebody who is somewhere who is like where we're really fast and efficient, and, you know, it could be a really big hammer if we do this right. Some more words about Vampire. It's a first order system. It is extended with a bunch of stuff like reasoning with theories, induction, higher order logic. We will focus today on this first order part. It's a saturation based theory prover. So we are trying to saturate, and then it employs a number of techniques to get us, you know, to get the medals, essentially. So it has to be efficient. One of the techniques that I would like to tell you a little bit more about is avatar. So let's hope I have the time to walk you through that one. Okay, now why output Vampire proofs to Didacti? Wait, I already have that one. Why Didacti, right? This was the slide that I want to tell you. I am now officially preaching to the choir. So you're my choir, and you can read with me the following reasons. So dear choir, we're doing this for interoperability, because it has a small trusted kernel. It's an ITP, so by default, the trusted code base is then smaller, and because it is powerful enough to express our language, which is essentially first order logic at this point. So dear choir, thank you for following me on this one. Additionally, maybe a comment for you, the experts. We are choosing Didacti because it scales reasonably well. So as far as I understand, and you correct me if I'm wrong, it's designed to machine check large proofs. So we actually, in our experiments, tested the limits a little bit. We had to increase the stag because Vampire produces sometimes quite large proofs. I'm saying here, unlike lambda pi, so this is the alternative one, which may be better for interoperability. So, you know, we are currently choosing Didacti for speed, but if it turns out that lambda pi is better, we might have to switch. So we will see how that goes in future. But essentially, you know, the principles should be the same as far as I'm concerned. So they are two concrete syntaxes of essentially the same theory behind. Okay. Now, what are we doing and how we're doing it, right? So concretely, we have this proof format. It's like a flag minus p deducti on vampire. So if you call a vampire with your encoded problem and you put a flag minus p deducti and you put additional flag to give you more details in the proofs, so elaborate the proof trace, so to say, we should get something that we can then pipe into the deducti checker, right? So it's basically hard-coded into vampire that it can emit proofs directly in the deducti format. So we're using what I call standard deducti encoding of first-order logic, the one that I got from Frederick at some point. So it's been tried and tested, and we are encoding concrete instances of the inferences that vampire uses. So not the general schema, but for every deduction step, for every inference, we are encoding the concrete one with the substitutions and all. Like I said before, sometimes we need to store some extra information. This is why we have the proof extra full. I will hopefully tell you a bit more about that later. Essentially, we're trying to minimize what we have to store during proof search, right? And then recompute some stuff during proof printing time. So we can have this discussion later. But just so that you're aware of, you know, there is no free lunch. You have to, you know, if you want to have more elaborated proofs than the default proof traces, we need to do something about it. Okay. Now I'm planning using the standard encoding of first order logic. Don't read this entirely. It should be something you've already seen and known. I want to highlight maybe a couple of things that are different from the traditional presentation. So one thing we chose to do was to encode our disjunction, so or, and here is the rewrite rule for or. Usually it has something a bit more general than proof of false here, right? So it's proof of P, arrow, proof of false, and then proof of Q, arrow, proof of false, and then goes to proof of false. This is like the general form instantiated with a proposition false here instead of a general one. Why we chose to do this is, first of all, because it really improved readability of our proofs when we were decoding it, because it was somewhat easier to do this. And second of all, it was sufficient for our inferences to work with just that. So it's still sound, it's just an instantiation of the general or, but we found it to be easier to work with. So if so far we didn't encounter any problems, I believe it can be generalized if necessary, if in the future we need something a bit more general, but I didn't see the use case so far. The other thing is that we have here an explicit inhabit. So the automated theorem provers pretend that all of the domains, so the domains over which we quantify are inhabited, they have at least one element. They don't really, they do this kind of under the hood. And when we were proof printing, we realized we actually need this explicitly, and this has recently also been added to the standard encoding. So, but we really realized that we actually need it explicitly. The equality here is the Leibniz encoding, and because we will support polymorphism, it's the polymorphic kind. So here it also takes the parameter that is a sort to the equality, but otherwise it's the usual one. I'm just showing you that the quantifiers are encoded as usual. The one thing that we added was the polymorphic quantifier because we wanted to support polymorphism, and that one was missing. But essentially, all of these things that are on this slide is all there is of the encoding, right? So as I was saying, you want to have something that is easily verifiable, where the axioms are fitting on one slide. So that's good. Additionally, we have some nice to haves. So again, don't read this in detail. They're basically notations to handle clauses so that we had some ease of actually doing the proof printing. What I maybe will here emphasize is that when we are encoding a clause, if we have like a literal and then cons another clause, this will just rewrite to the usual encoding of disjunctioning clauses. So proof of P, arrow proof of false. So proof of the literal, arrow proof of false. And this thing will appear everywhere during our proofs. So this is maybe something we can keep in mind, especially if we look at the avatar encoding later. We use the same trick for encoding clauses also for avatar. So here we have something called AV clause. It stands for avatar clause. Essentially, it does the same trick. We are adding more implications on top and stacking them, and it actually behaves very similarly. But maybe unlike here, when we have so the empty clause, where do I have it? Yes, here. The empty clause EC here will rewrite to proof of false, and the empty clause in avatar will rewrite to the regular clause that avatar was over it, right? Around it was like on top of the regular clause. But essentially it's the same trick. And if you don't understand what I mean by this avatar clause, you will see it in a couple of slides. Okay. The main point about this slide is that all of these shorthand notations, as I see them, all of this rewrites and normalizes to the encoding of first order logic that we had on the previous slide. So we did not introduce any new axioms at all. We are just using the same thing, just with some support for proof printing. Okay. Now, the most important slide is what we can actually do so far. So we can, this is a trivial one, parse the input problem. So we can read the input problem as specified in the TPTP or SMTD format that you give to Vampire. And then we extract that to the didactic axioms. And then once we've done that, we can run Vampire basically in default mode and fully check these reasoning steps. And I listed them here explicitly because then people ask me, what inferences have you done already? Well, these are essentially the ones that appear in the default mode. Here, avatar, recently we have completed the entire proof of avatar, which also involves some parsing of SAT proofs. So this was a really cool thing in my opinion. The other ones were, the theory was there before. So resolution, superposition, nothing that we haven't seen before. Maybe additionally, we had to do some simultaneous substitutions because Vampire behaves that way, but it wasn't too bad. Additionally, we also now support many sorted logic and polymorphism. So that's why we had the polymorphic equality and quantifier there. Because you are very well experienced, you might want to say, are you really supporting all of the inferences? So there are some temporary, I call them temporary limitations, because I believe some of them can be done away with. We have limited preprocessing in the sense that the clausification is not checked yet. This is, a bit disappointing at first, but we have some ideas how to do this in the future. Maybe we can also discuss them. I have some ideas on the last slide if time permits. But we do have, you can give it a full first order formula. It can be parsed, the axioms are there, but the classification steps are not checked. So we insert a sorry axiom there. And also it will emit a warning when such a sorry step is present. The other thing we can't do yet is higher order reasoning and theories. This is not done yet. And we had to turn off all of the fun bits, so to say. So only the inferences that were on the other slides are supported. But the positive thing is that inferences are done incrementally. So you can just tackle one inference at a time and you have more and more trust in your proofs. And like I said, we have this sorry axiom for which we emit a warning. So there is a print in the didactic syntax so that when you run the didactic type checker, it will actually print out a warning. So you're aware that, it's not a full proof yet. Okay. Some lessons we have learned during the implementation. I will name two that were interesting, implementationally just. Equality is really symmetric. And actually, Vampire believes it's symmetric, so it will switch the left-hand side and the right-hand side of the equality when convenient. For proof printing, this appears a bit problematic because in Deducti, in our Leibniz encoding, it's not symmetric by definition, but we can prove the commutativity lemmas. And in practice, we had to manually insert all of the commutativity lemmas during proof printing. So this was a bit of work on top, but it's not that much. It's just for the things that actually appear in the proof, which is much less than the things that appear during entire proof search stage. But we had to pay attention to that, and it was a bit tricky. The other thing that we found really useful while implementing was that we were numbering our deduction steps in the Deducti output according to what number they had in the original proof trace. And if we have an unsoundness bug, for example, it's much easier to then follow, because Deducti proof script can be quite involved and long because it's very detailed. It's then easier to pinpoint exactly which rule and which arguments are problematic. So you can really see the one-to-one correspondence between the default proof trace that is emitted by Vampire and the Deducti output that uses the same numbering of deduction steps. So this is just, if you're planning to implement something like this, would recommend to have the same numbering. Okay, now I want to tell you a few words about this avatar technique that we have. I'm using this as an example because all of the other ones are somewhat trivial compared to what was already done, and you have probably already seen this is something that we really had to do ourselves, and I think it's kind of fun. And we will also show some of the tricky bits when we're implementing such a thing. So for those of you who don't know what Avatar does, here's a brief introduction. So it's a technique that really improves the efficiency of first order reasoning. And it does so by splitting clauses and then offloading this disjunctive structure that we have to a SAT solver, right? So if we were trying to do any proof checking, we also need to deal with this SAT solver proof on top. Now, for proof logging, what the relevant part of the splitting clauses is that essentially this is like introducing propositional labels to sub-clauses that appear in the proof. And here are actually the inferences that we have to deal with. So I said that a definition is like a propositional label. So we can have something like, I call it SP for split. So split 1 will be some subformula. Split 2 will be another subformula. And this will also have to be dealt with when we are translating to Deducti. And then the actual split is, so for example, if we have a clause like this, we will split it into components, right? So split 1 or split 2. And here we actually grouping these literals in the clause according to which variables appear. So they have to be variable disjoint components. So here, for example, we have two splits. So one is the one with P and FX, the other one with the Q, because they both share a variable, and the third one doesn't share a variable, so it's a separate component. And then, I'm sorry, the Zoom comments are in my way. I'm so sorry. Okay, so the third inference is the component inference. So all of these components that we split into are added to the search space as a conditional clause, right? So we have this clause conditionally on this propositional label, and this clause here if the propositional label SP2 holds. Then we have what we call an avatar clause. So all of the derivations that are done afterwards that include these, that include these propositional ifs have to also be conditional to the propositional labels. So every derivation that has a premise of this sort will also have to have some condition on the side. And then there are two more. One is from every conditional clause, so to say, we want to derive false. So it will be a derivation conditionally on a split clause. And then what we actually deduce from that is a set clause, this split, right? Because this is false if this, so obviously this. And then the very last step of this avatar is the refutation step. So it actually, from all of these SAT clauses that we derived from local contradictions, so to say, you have to derive the very last false, and it will derive false because the SAT set is unsatisfiable, right? And this is where we have to incorporate this SAT proof. Now, we can handle all of these things in Didacti quite easily. So the definitions that you saw on the previous slide, it's just a Didacti definition. We can basically include a very, the simplest of the rewrite rules, just a definition, and we introduce a new symbol that maps to the propositional label we wanted. And then for the splits, we have to unpack variable renaming and apply variables and literals to the premise. So for example, this here is the split that I had on the previous slide, right? So we introduced two propositional labels. Now from this premise that this is like the encoding of the clause here in Didacti, and these square brackets are essentially just proof of this literal to proof of false, the one that I also highlighted in the first order logic encoding. If we have an encoding of the premise, this one, we have to derive the conclusion, which is this one, which is basically split one or split two, right? And essentially, this is just application of the premise here. So here you can see C is the premise clause and then applies to all of the arguments. But these arguments have to be bound on correct places, because when we were introducing these propositional labels, we could do some variable renaming, and we could do like different order depending on how variables appear. So it's basically a shuffling of where variables appear. So it's not too bad, but we have to be very careful how the splits are introduced. Then the avatar clause will just be, this conditional clause will basically tag two more literals, which are these propositional labels in front. So it's just almost a regular clause. And for this one, we're using this avatar clause shorthand notation that was really helpful. And then the component clause is just the identity function, more or less. The contradiction will then just be the premise, because we have tagged this in such a way that it will directly correspond to the premise with which we did this. So here, when we have the contradiction, this one, essentially what I'm saying is that the encoding of this conclusion in this rule is almost the same as the encoding of the premise. So it's really a no-brainer then in the implementation. And then the very last step, the refutation step, where we have to involve the set proof, is a bit more involved. So here on the next slide, I want to tell you essentially what happened. What happened was that by default, Vampire ships with a copy of the SAT solver minisat that does not emit proofs, right? So if we want to get our hands on the actual proof, our hands were tied. We couldn't do it from the default one. To rectify the situation, well, what you want to do is replace this minisat guy with somebody who is a bit more verbose and will give me some certificates. Okay, so we added a new SAT solver, which was Cadical, because it can emit DRAT proofs, but in practice, only the reverse unit propagation, so I'll call them RUP proofs, are used. Okay, so we have to deal with these RUP proofs in the Didacti encoding, not the full DRAT proofs, at least at this stage. Incidentally, Minisat, because it's simpler, it turns out it works better for the kind of problem Avatar produces, right? So Cadical is a bit smarter, so to say. So it wants to do more. So initially, in the first few seconds of running, it's a bit slower, but Minisat is already done on the simple problems by then. So we didn't want to just encode Cadical as a replacement of Minisat. What we did indeed was when we're doing the proof extra thing, Cadical will compute again just the last part where Minisat is succeeding to get like the end false proof, right? So just once in the end, we will recompute that one part that we already know can succeed, so we can spare a few milliseconds. And we will get the reverse unit propagation proofs, and in the proof extra thing, we will just store the intermediate SAT clauses. And in the proof printing stage, once we are done with collecting the extra bits of information, we will replay this reverse unit propagation just for these SAT clauses, because we know that we will succeed. And in practice, they're usually just like 5 or 6 SAT clauses that are for one step of reverse unit propagation. So this RUP proof will morally just be a change of resolution. So nothing new had to be invented here to actually replay them in Didacti. The tricky bit was actually getting our hands on the relevant information. So enough hints, which are the intermediate SAT clauses. And then the resolution proof looks just like ordinary resolution, but with these propositional labels in place of literals. Okay, and the very last part that we have to check is that it ends in the proof of false. And if it ends in proof of false, then the entire proof ends in proof of false, which is what we want to do for vampire proofs. Okay, now that we have our hands on all of this information, I want to convince you that this trust base is a bit smaller, right? So when we are doing proof checking, there are certain things that we have to trust, and there are certain things that we can check. So what we do have to manually check in this setting, right, is that, well, the encoded first order logic in the file, in the Didacti file, corresponds one-to-one to what I showed you on the previous slide. So we didn't change anything. And you can inspect it, and it's, I will call it a standard one, and it just should be there. The second trivial thing to check is that the encoding of the problem axioms and the negated conjecture, so the thing that's actually was given by the user as the problem, are also encoded correctly. Otherwise, the Didacti proof script will essentially prove the wrong thing, which we don't want. So these two are fairly trivial. It's just a couple of lines of check. And this, you have to do it like with your own eyes. The third thing that we need to check is that all of the symbols that are introduced after the axioms are defined, right? So that we don't have any additional axioms, which include sorries. So we should check that there are no sorries if we want to have the real big trust in the proof. And another thing, that there are no rewrite rules after the encoding of first order logic, right? So I'm saying this with a grain of salt because a definition is technically a rewrite rule, but it's the trivial one, right? Anything non-trivial with some pattern matching or something is disallowed. Otherwise, we cannot claim any soundness. And then if we do all this, the only thing that is left to trust is the Didacti type checker, which I made the point that has, a small enough kernel, and, I trust Didacti much more than I trust my own human checking and filling in the details, especially for the problems of that size. So this is about the trust part. The proof extra part, what we have to store additionally here, I'm just listing what we wanted to carry. So the point here is that, as I say here, we want to minimize what we need to carry around during proof search. So before we succeed in finding proof, so we really want to just carry around hints so that we can recompute later in full detail and deterministically without proof searching, more or less, what what was going on. So for resolution, for example, just the selected literal, and then you can more or less deterministically compute the rest. Similar to the other ones, the thing that we do recompute at the proof output stage. So once the search is done, once Vampire says, okay, I have succeeded, I found the proof, now please give me the proof, we do recompute the substitutions. So we collected hints during proof search, we recompute the substitutions. And as I mentioned sooner, we do recompute the reverse unit propagation steps for the refutation, for the last refutation step, the one that SAT solver emitted, right? So this was, but it's quite minimal recomputing compared to like doing actual proof search for every intermediate formula that it is derived from the premises. So it's much more deterministic. It's recomputation, not reproof searching, more or less. Okay, let me show you some experimental data. Now that we have the implementation, we ran some experiments on how much slower this is. So we ran it on the TP library, version 9. We input all of these CNF first order formulas, TF0 and TF1 fragments. We excluded the ones that are non-theorems, so satisfiable problems. And we excluded all of the ones that have arithmetic in because we cannot support it. We ran Vampire with its default strategies. We only replaced the non-deterministic part with a stable one. So really essentially just the default strategy. And so here is one caveat about these experiments. I'm showing you what we ran before avatar refutation proof. So the SAT solver part was done. Now we're rerunning the examples, the benchmarks again, and we will see how much the very last SAT solving part slows it down. I want to specify here that the avatar fully was involved in proof checking, just the proof printing of the SAT proof was not done in the experiment. Okay, so it's just the additional overhead on proof printing that might be missing for this last step. So some results, we gave it instruction limits. So this corresponds to essentially like 7 seconds per proof that we gave it. And with the additional proof extra information we have to store, we managed to prove just 5 problems fewer than the total almost 8,000 in the default one. So we weren't penalized at all by very much because we were storing extra information. The important part here is that all proofs were successfully checked by Didacti. Modulo sorries, right? But we did test the limits a bit, so we had to increase the stack for some problems because we were pushing Didacti to the limits with the size of the proofs. Here are some graphs that are somewhat informative. So this one is maybe interesting. It compares the time that is spent on proof printing. So this is finding the proof without the printing, and this is just finding the proof and also printing the old spaghetti code that comes from Didacti. And this one is, essentially it's almost okay, mostly just like 25% longer it takes to also print the proof. Somewhere here are the real, 10-fold, 100-fold, 1,000-fold slowdowns because the proofs are so big. The actual proof printing time counts and it's slowing this thing down. So I think this was okay. Proofs are long, so it's going to create some overhead, and just 25% for the actual printing is not too bad. Now, a few statistics on actually proof checking. So this was just proof printing. Then once we run the decay check on the size of the proof, the median time for actual checking was quite low, a few milliseconds. The average time, a little under a second for the 8,000 almost proof that we did. And the maximum time for the long and involved one was 42 minutes. So we were, we have some benchmarks now to also check Didacti capabilities. Now, these two graphs are semi-informative. So this one shows how the file size compares to the time that we needed to generate it. So it's okay asymptotically. This one compares the time compared to the number of proof steps in the proof. I would say that both of these are somewhat uninformative because the file size can really depend on what the encoding was. So if you change the encoding, you can, reduce the file size by half or even more. So, it has its issues. Similar for proof steps, like some proof steps are really long, some proof steps are just a definition from before. So it's also semi-informative. If you have any better properties that you would like to measure about these proofs, please let us know, because we are aware that these are problematic, but we don't really have a better estimate on what would be interesting to see. So, reach out to us if you want to see some other measurement that would be relevant. Okay, so one more note about the constructive proofs. Actually, all of the inferences so far were constructive. We didn't use any classical axioms. We didn't check classification. So apart from that, I was surprised that Avadar didn't use any classical axioms. I was quite sure that that part with all of the SAT solving would do something interesting, but actually it was okay. We have to note that what we output in the end is the proof of double negation. So we prove that from the negated conjecture follows false, but we don't actually deduce the conjecture. So, the theory says that the double negation translation makes it such that it's always possible to just have a classical proof and then have just one classical step, the elimination of double negation at the end. So this is what wasn't too surprising. The theory says it's possible. I find it nice that this was, an illustration of that in practice, that, all that was left was the last classical step that vampire doesn't do, but we can as humans on top. Okay, now I think I'm doing okay on the time. I have some speculations on currently unsupported inferences here, but maybe I will just stop here and talk to you offline about these, because I want to give the other speakers sufficient time for discussion. So at this point, I would just maybe thank you all again for staying with me, bearing with me, and welcome any questions you have.
Very much. Questions? Melanie?
So you just said you don't want to talk about the unsupported things, but I'm a bit curious. So maybe just one quick question: do you feel like there are any conceptual hurdles to encoding those, or is it just more work that has to be done, and you're confident that there won't be any challenges or issues?
Mm-hmm. Okay, now that you mentioned it, I do have a spare slide, and this is really speculations and it's open for discussion. But okay, so first thing that I wanted to say is that many classification rules are just straightforward. So we encoded a couple of examples already, and it's just, it was straightforward. It was just extra work. And some more details in the proof extra. So we would have to traverse the formula and then just do the work. The tricky ones, right? This columnization one, I always hear this, but it's only preserved satisfiability, not probability. For me, there is no free lunch. So I was talking to some of the type theorist crowd around, and I was asking them, so what would you do, right? Because essentially columnization requires some classical axioms if you want to turn it into provability. So I thought, and like not just we, my co-authors included, thought of a few approaches. So one would be just posing an axiom of choice in full like this. So have the actual choice function choose that gives me the actual element that we are choosing, and then having the proof of this predicate on choose function to be true. This is one way of doing it. It might be too big of a hammer to the theory. So the other way we could do it is maybe not as general as this, but posing only the instances of the axiom of choice that are needed for columnization that appears, right? So I wouldn't have this general form, but I would pose basically the proofs of the columnized constant, so to say, only the instances which appear in the proof. And this is better because if you have a very nice theory, you can, for example, in the optimistic scenario that this is used as a hammer in an interactive theory prover, you can then leave these as open lemmas to be proven. And if your theory is nice enough, maybe they can be proven without axiomatizing the full axiom of choice. And so that could be the other option. And like these two ideas I had, that we can actually do something within this provability scope but like not overkilling it with the actual axiom of choice. But like I said, I don't think there's free lunch. If you wanna just encode this as provability, you'll have to have some compromise, so to say. The other thing that we were also thinking about is the technique called polarity flip. So essentially, if we just flip the polarity of all of the literals, we can argue that it has the same models. This could be just essentially exploiting the deductive definitions. So we can define a polarity flipped thing and then just proceed with the polarity flipped literal in the following. And because it will sort of unfold to the correct thing, it shouldn't, like, the proof shouldn't be impacted that much. So I think this definition on top could take care of the polarity flip. And there are also some other things that use the same trick, like also Avatar was using the same trick, right? We introduced a definition and then we rewrote it to the correct thing and handled it properly. And many of these other inferences that Vampire uses are of that form. So we could really expand the number of inferences we support by using this trick further. Yeah, so some of these, like I said, are more involved, like, giving additional axioms. Some of these are really just, exploiting that, like what Didactic can do for us. Also for the theories, that's maybe another issue. It's also the issue of how efficiently these theories are represented in Didactic or LambdaPy, right? So LambdaPy has some further support for that, which for me is a good motivation to maybe switch to that concrete syntax. And test the limits of big proofs on that. But I'm open for suggestions. If anybody has done something that can be useful, I'm all ears. Yeah, but thank you for the question. It was a really good question, and you gave me the opportunity to share my extra slides. So thanks.
There's another question from Sophie.
Yeah, so actually it's a question, but first a comment about scholemization. Because in lambda superposition, what we did, so not the higher order superposition that is in Vampire, but the one that was designed for superposition. What we do is maybe a bit similar to the second option you introduced, is we consider the Skolem symbols as uninterpreted symbols, and we extend the signature that we have inductively.
Mm-hmm. Yes.
So I guess it goes also in the direction of the second point. So
yes, yes.
Yeah. So my question was on a different direction. It was, so you were doing this for Vampire's rules, but there are other superposition engines around, like E and superposition. How specific is your work to Vampire, and how do you have an idea of how, if it could be useful to also get proof certification in the other superposition provers?
I think many of these techniques translate. So, we didn't reinvent, encoding of the resolution proofs and superposition proofs and so on. This has been done by Guillaume Brel years ago, for example. So, what we really tried was to encode them in this big prover. The technique that we had on top were concerning how to store extra information, which I think would translate to, like, if you're using resolution step, you can just, use the same trick, just store this piece of information and then translate it, find the substitution in the end in the same way. So I think such techniques are really exportable to other things. I don't know if anybody else does the avatar. So that one was maybe more specific to vampire.
You have some variants of avatar in ZPerposition and in E also.
Yes, so you can use essentially the same encoding, right? I showed you how to introduce a split, how to like then replay the proof, and then you can implement the same technique. Yes, I think those things are exportable to other provers. Yeah.
Sorry, the work involved would be to make sure the informations are outputted by your proof output, and then it would be just a matter of parsing it to your deductive engine. Or to your
yeah, so maybe I should elaborate on that a bit more. So there are two parts that are required for this proof output. One is that you need to store some additional information during proof search. Like I said, which literal is being used in for example, in a resolution proof and so on. And then the other one is recomputing the substitutions needed to emit the actual deductive term, right? And the way your prover computes the substitutions is important, right? Because then having the index of the literal that plays the crucial role, for example, in resolution proof, you need to be able to recompute these substitutions according to how your prover works. So, and that is specific to how you're handling certain things. So, okay. but the idea is the same, right? So I'm telling you which things you should or could store to improve efficiency, and which things are then recomputed. And I'm also showing you how the end deductive term looks like for example, for vampire in this case, right? So you can essentially do the same thing, but how you get to the actual substitution map, the unifier map, depends on your concrete implementation of the prover. Yes. Thanks for the really good question. Yeah.
And I have a question that's quite boring, but if one wanted to find the foundations of vampire to check that it matches the deductive encoding and stuff, where would I find that paper?
I'm not sure what the question means. So are you asking for a reference that presents all of the rules vampire, like the vampire inferences?
Yes, exactly, precisely. And these mechanisms for avatars and scolumization and such.
Yes, okay. So this is just, I forgot the name of the paper, but it exists. Avatar is a separate paper. So the easiest one, I would say, actually we have a preprint available of this work on arXiv, and we cite the relevant avatar paper and the relevant vampire paper. There has also been on CAV this year was a paper called the Vampire Diary, I think, and it also gives the overview of all of the new features that were not present in the previous papers, and were, it's for kind of like an overview of a technical report of what has been done and what other techniques are available now. So there's definitely lots of literature there.
Cool.
Yeah.
And you say that the preprint, so this means this will be published later this year or something?
The paper you want for the base of Vampire is a paper by Voronkov and Kovač from 2014.
Okay, excellent. Yeah. And I was asking specifically just then about, you said that you have a preprint for this work as well?
Yeah, so it's on arXiv. The title of the paper is the same as the title of this talk. So you can find it on arXiv. Hopefully it will be published somewhere. It was submitted for publication, so we will see. But at this stage today, I can just say, like, you can have the preprint. It's available on arXiv. Yeah, you can find it.
Thank you.
More questions?
One question versus comment. I think I discussed that with Michael at SMT or another conf before, but maybe the things that you do with Minisat and asking for the SAT proof afterwards is not a bad thing. You did it because of constraints, but maybe this is not a bad thing at all, because there's no need to look for a proof when, well, before you have actually proved, right? So it doesn't cost much. The thing is that I did in, it doesn't cost much either to modify Minisat so that it actually produce resolution proofs. It's really not that complicated. It's just a few tens of lines of code. But
I'm sure I'm not sure. I've been wondering, I think you are using LRAD proofs, right? Or LROOP proofs instead of ROOP proofs. Because you want resolution proofs, so I think you are using LROOP, even if you never mentioned it.
So I think the default is DRAT for Cadical, but they say they only, and so far they have only done like the ROOP part.
Yeah, but
it
can give you directly resolution proofs.
Okay, even better.
But Minisat can also produce resolution proof without any problem. It's really, I mean, if you cut the pre-processing stuff, there's no the engine.
As far as I understand, and maybe so, I think Michael is on the call, so he's more of an expert on this stat solving part. I was more of the type theorist part. So maybe he can jump in. But as far as I understand, the version that is shipped with Vampire of Minisat is, cut sufficiently so that it's minimal enough to be very fast for Vampire needs, right? So I'm pretty sure we can play with what stat solver is used there, but I'm wondering, will it cost us efficiency? Because if we're doing this, doing proof search many times, then you want this to be really fast. And like you said at the end, if you just for the last part rerun the search with something a bit more elaborate, it can be in any form I want, right? So I think we also have to pay attention to this trade-off between efficiency during proof search and switching for a different stat solver that would give us more information.
Yeah, the point is,
I can say that the Minisat
Michael,
I have trouble
unfortunately,
hearing
your
you.
microphone is cutting out a bit.
Yeah, we can't hear you at all.
And also, we're running over a bit on time. So should we perhaps move on, or?
I think this is fine. Since we are not physically there, I would love to say, contact us during coffee break and we can continue the discussion. Since I cannot do that, please email us and we can continue the discussion over there and get in touch afterwards. I really appreciate all of the suggestions and comments, and please do take the time to reach out to us. Maybe, even later if you are busy actually socializing during coffee breaks and hanging on your computer or phone. Okay, but thanks so much for all of the questions and for being such a lovely audience. And I hope to see you soon in person.
And thank you so much for your talk. And now